Ladies and gentlemen, hello and welcome. Coming to you once again, not quite live from One Take Studios, where today's topic is radical functions, which is a totally radical topic, man. Seriously. Okay, some people actually don't know what radical means for math. That's going to be anything with a sign that looks something like this. This is called a radical sign. So square roots, cube roots, fourth roots. Yes, there are things that exist besides square roots, people, and you're going to see two things today, square roots and cube roots specifically. So why, pray tell then, is there an x squared? Why do we have a quadratic graph sitting here? Because I want to show you how much the world of math actually makes sense. All right, this is the graph of x squared and using actual points, so it's not a sketch, it's a real graph. If I find the inverse graph for this one here, again, the foundation of all things inverse is to have the x's and y's switch places. So this point, for example, is 2, 4. So if I'm looking for the inverse, instead of 2, 4, I'm going to go 1, 2, 3, 4, 1, 2, and that point's going to go right here. 1, 1, if I switch points, is still 1, 1, so that's actually going to hit right there. 0, 0, same thing, switch points. This one is negative 1, 1, so I'm going to go 1, negative 1 instead, and negative 2, 4 becomes 4, negative 2. Check it out. What do you see? Ladies and gentlemen, the inverse of f of x equals x squared. Sorry, I'm having trouble seeing through my own hand. Okay, it's not terrible, but it's not the best I've ever drawn. Please forgive me. There we go. Is this graph right here? All right, so this is the inverse of x squared based on the graph. This, however, is not the same as this graph is going to be. And here's the reason. Notice again the topic is radical functions. We're talking about functions here. And this red parabola is delightful looking, but it's not going to pass a vertical line test. It's not a function. So the inverse of a parabola is a sideways parabola, if you want to call it that, but the square root function, which would be the inverse operation for x squared, is a little bit different. Let's think about why, shall we? All right, so the graph here, if we look at this, what is the square root of 0? 0. So origin, again, is going to be our point. The square root of 1 is 1. 1, 2, 3, 4. The square root of 4 is 2. So notice so far these are lining up relatively well. Okay. Why can't we go square root of negative? Because we can't take the square root of a negative. Why, when we go the square root of 1, did we not also say negative 1? Rule of thumb says that if the radical sign is part of the original problem, we don't go with a plus or minus response. The flip side to that is if you have to put the radical sign in yourself, say you're actually solving a problem with quadratics, then you want to do plus or minus. So because we would like this to be a function, and because the radical was part of the original problem, the graph for a square root function is actually half of a parabola. So instead of saying, oh, it looks just like a funny line sort of curve thing, no, it's actually half of a parabola, which makes sense because it is the inverse for quadratic. All right, so this is the inverse graph for a parabola. This is actually the inverse function. So f of x equals square root of x, boom, there we go. What does this mean about our domain and range? Usually for a parabola, the domain is unlimited. It's going to be all real numbers. We can't say that here with domain or range because we have a distinct starting point. This is a point here. That's an arrow there. It only goes one way. So what does that mean about the x's? Well, let's see. Here's the x-axis, starts at 0, goes to the right. So that means x is such that x's are greater than or equal to 0. Again, so that's just formal notation, the set of numbers x such that x is greater than or equal to 0. Well, what does that mean for the y's for this? Same kind of thing. If here's my y-axis, the first one's at 0 and everything is up above that. So the y's are also greater than or equal to 0 in this case. All right, so this is our parent function, and this is without making too many alterations to life. This is what we should expect to see. So if you see square root function, your brain needs to think half of a sideways parabola. That's the image you should have. And from there, we might make alterations to it, but that's always our starting point. All right, on a similar topic, what does that mean for cube root graphs? All right, so cube root graphs. Let's go ahead and draw this one in here. I don't have it started yet. 1 cubed is 1. Oops, I'm not going to do that though. I'm going to count on my y-axis by 2's because this gets really out of control really fast. 2, 4, 6, 8. All right, and then my x-axis, I'm just going to count 1, 2, 3, 4 still. All right, so if I cubed 1, it's 1, so that's actually going to put me right here. If I cube 2, that's 8, so that's going to put me here. 0 cubed is 0. Negative 1 cubed, think about that as negative 1 times negative 1 times negative 1, so that's negative. And same thing here, negative 2, 2, 4, 6, 8. There we go. So this is our delightful, there we go, there we go, there we go, our delightful cubic graph. Again, also known as a travolta, as I will show you again why that is if you missed it in one of my previous videos. Okay, I'm serious. This graph doesn't have a name. Start calling them travoltas. It's what they are. So, what does that mean for the inverse? What does that mean if I would like to do the inverse? And I'm actually going to do an inverse notation very specifically here. The inverse operation for a cube is a cube root. Again, inverse operations are operations that undo each other. So a square root will undo a square, a cube root will undo a cube. Please notice the difference between a square root and a cube root, because if you're not paying attention, you're going to miss it. Square root is so common, we don't put the little tiny 2 out front. It's called an index number. So if there's no number out front, it's automatically a square root. But if it's not a square root, you have to have the index number. So this one has a 3 to show that we are doing the cube root. In other words, what number times itself 3 times would actually make this sort of thing happen. So if I reverse that thought process, the cube root of 0 is 0. The cube root of 1, 1 times 1 times 1, that's still going to be 1, 1. So that point is also part of the inverse. Remember this point here was 2, 8. I should have counted that the other way, shouldn't I? Oh, that makes me so sad. Oh well, I messed up. So this is going to be, if this is 2h, we're going to go h 2. Is it too late to change my life? A little bit. Okay, I'm sorry about that. So we're going to go with h2. So 4, 5, 6, 7, 8. 2 is right here. And then, if this was going to be negative 2, negative 8, we're going to go with negative 8, raw, way out here, negative 2, okay, so it's, I give up, I'm going home soon. Alright, what I need is this guy's going to be way up this direction, so I'm going to make it go like this. Check it out, check it out, check it out. There we go. I'm going to shorten this up for the sake of life. Ladies and gents, that is the inverse graph. And it's a function this time. So in this case, the red graph and the blue graph are both functions. So x cubed, its inverse, cube root of x, same thing. We don't need a separate graph. We don't need to make sure that it is a function because it is a function. That's it. So if the blue is a Travolta doing his dance moves, then the red is what I would call sleeping Travolta. He dances in his sleep. Okay, maybe not. Don't tell him I said that. So, what does that mean about domain and range? Well, for the blue graph, it's going to keep going up, keep going down, so there's nothing to stop the range. It's going to keep slowly moving outward, left and right. There's nothing to stop it. So this thing has domain and range of all real numbers. So when I do the inverse, and we talk about domain and range switching, just like x's and y's switch for inverse, it's still going to be the same. There's nothing stopping the red graph either. It's going to keep going left and right. It's going to keep subtly going up and down. So this is x's such that x is a member of, that funny looking sort of curved e thing, is a member of the set of real numbers. And that is a double stemmed r. That is our official notation. So x is a member of the set of real numbers. And the same thing, y is also a member of the set of real numbers. Ta-dum, ta-dum, ta-dum. So domain and range, cube root, always all real numbers, nothing to stop it. Square roots, squares, a little bit different because we've got a vertex which sort of limits things, and in the case of a square root, we've got two limitations on both domain and range. Alright, so that is the overall gist of things. What I want to show you then is a topic of conversation that we might have if we were to then take this and view it from the perspective of transformations. So ladies and gents, right now I've got the square root of x on my screen. We can see that. That's our sideways half parabola. Again, it's half of the parabola because it needs to be a function. So what does that mean if I change it slightly? The next equation that we've got here, can I make this work? I can, there we go. I typed the square root of x plus 2. So I want you to think about that for a second. We talk about h and k left and right movement. So this is transformations is a topic that we've talked about before. This means that I'm taking all of the x values and I'm changing them. That's a transformation. If I'm changing the x values, should that slide me left, right, or up, down? If I'm changing the x's, that should be a left-right movement. And again, because it's x plus 2, but we're seeing this from y's perspective, a plus 2 actually means 2 to the left. Boom, there we go. So under the radical, if we are affecting the x value, we can see left-right movements. So that is a translation, a horizontal translation to be specific. If I go here, this one, there we go. All right, so that is the cube root of x. And again, we can see our sleeping Travolta here on his side, taking a nap, doing his disco dance moves. What happens if I go to this instead? Now notice this time the plus 2 is not in the same spot as last time. This makes a difference. The last time the plus 2 was under the radical with the x and affecting the x's. This time it's outside of the radical. In other words, after we finish calculating this, we're going to add 2. That's going to change our output or our y values. And because we are looking at things from y's perspective, if we add 2, what should happen? Did you say everything should go up 2? I hope so, because there we go. So this is my k, if we talk about h and k. So previously, in the previous slide, we had x. This one is k, and this is in charge of my up-down movement for things. Same exact graph, just slid over a bit. And to prove my point, I told you that this man is a cubic graph. That's why I call them Travoltas. And technically, yes, this is a cube graph and not a cube root graph. But humor me, because I'm also making the point of what happens, what did I do to actually make this match up? Yes, it's x cubed, but it's got a negative, so that means I reflected it, flipped it over the x or the y-axis. In this case, actually flipping it over the x or the y achieves the same effect. And then I did a 0.3. So what is that? That is a vertical compression to make it fit his arms. And this same type of thing with reflections and compressions and stretches also affects my cube root and square root graphs. All right? That entertains me. Okay, so back to my other page here, just to make sure that we've got all the bases covered. There we go. All right, so please take a look at this. This is what I was just talking about. I'm not going into this in great detail because this is a previous topic that we have worked our way through. So what I'm saying is very much like what we saw for parabolas. We did this intensely for parabolas. It also works for square roots or cube roots for that matter. The a in front controls your stretches and compressions and reflections, so we see that. The x minus h in the parabola setting was in the parentheses. In the radical setting is under the radical, and again controls left-right movement. It always appears to be the reverse of what it is because we are looking at left-right movement from the perspective of y. We haven't solved for y. And then the k is on the end. Here it was outside of the parentheses. Here it is outside of or past the radical. And this controls the output up and down. And it is as advertised. If it's plus, it goes up. If it's minus, it goes down. So that's just a review. And have fun with these graphs. I kind of enjoy them. All right? Thanks, guys.